We are in A2U7 lesson 6 and 7. I'm going to combine the two. So we are ready to start solving logarithmic equations. We're just going to start simple and work our way through, and I'll stop and address problems you might run into as we go along. So there's two different types of logarithmic equations. Your first one is the log to log. These are the easy ones. Now your steps in solving these are first to condense, then use a one-to-one property, and then solve. Alright, condensing is what we've been looking at. Using the one-to-one property. The one-to-one property says if log base b of m is equal to log base b of n, then m is equal to n. This is just like when we were solving exponential equations and we had like 3 to the x plus 5 power equals 3 to the 7 power. If your bases were the same, you could take those exponents and set them equal to each other and solve the equation. Same thing here. If your log bases match, then you can take the numbers here, make an equation out of them, and solve. So we look at this one. Our first step is to condense, but this is already condensed as much as it can be. So all I have to do is notice that the logs match. I can apply the one-to-one property and make an equation of 5x plus 9 is equal to 6x. Now I'm ready to solve. Subtract 5x from each side, so I get 9 is equal to x. And that's how you apply the one-to-one property. So let's look at another example. And here's our next problem. 3 times log base 7 of 4 is equal to log base 7 of 4x minus 8. Now our step 1 was to condense, and this one does need to be condensed. I know that because it has this coefficient out here. Now we use those properties to condense. This is going to take the power property. Remember it said if you have a coefficient out here, you can make that the power of this. So I'm going to rewrite this as log base 7 of 4 to the third power equals log base 7 of 4x minus 8. Now that it's in condensed form, I can use my one-to-one property and just state that 4 to the third is equal to 4x minus 8. Ready to solve. 4 to the third is 64 equals 4x minus 8. Add 8 to each side. And 64 plus 8 is 72 equals 4x. Divide both sides by 4. And x is equal to 18. Our second type of logarithmic equation is log to number. And that's what I have here. Log base 2 of x minus 4 equals 6. A logarithm to a number. And the method here is to condense first. Convert to exponential form. When we first started talking about logarithms, we learned this rule right here. That log base b of a equals x could be converted to exponential form by stating it as b to the x power is equal to a. And that's what I'm going to do here. I'm going to translate this. I'm going to convert this. My base is 2. Come over here. So now I have 2 to the 6th power is equal to x minus 4. And I'm just going to solve this. 2 to the 6th power, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. 2 more is 64 equals x minus 4. Add 4 to each side, and x is equal to 68. Okay, let's do another one. The first problem that we're going to run into with logarithms, and probably the biggest problem, is the concept of extraneous solutions. Sometimes when you get your answer, after you work the whole problem, the first thing you're supposed to do is plug that answer in and see if it works. And I know we get kind of lax about that. We just kind of get an answer, write it down, and go on. We don't think about it. But as you get up into higher level maths, you're going to find that sometimes you get answers that can't exist for one reason or another. The biggest reason is because of domain. The domain of any function is your set of x values. Those are the values that you are allowed to put in. Think of a domain like the concession stand. If I tell you to go to the concession stand and get me a Diet Coke, and you go down there and they don't have any, you can't get me one. Okay, they just don't have it. It's the same way with extraneous solutions. If you get an answer and that answer is not in the domain for that function, then you can't use that as an answer. And the easiest way to look at a domain is to look at a graph. Here I have a graph in blue of 10 to the x power, which is an exponential, and in black a graph of the log base 10 of x. Remember, we talked about the fact that exponentials and logarithms are opposites of each other. That's why these two graphs are actually mirror images, okay? They've been reflected. So let's just look at the domain and the range as far as characteristics go of both of these graphs. My domain on 10 to the x power, remember, it keeps on going to the left and it keeps on going to the right. So my domain of all my exponentials was the set of real numbers. Now my range, when I looked at my y-axis, my graph never went below the asymptote. So my range for the base function here was at y is greater than 0. That's the only thing that could be. Now let's look at the inverse function and see what happens to the domain and the range. On my logarithm function, when I'm going to x, both directions, x towards positive infinity and x towards negative infinity, it stops right here at the y-axis. So my x has to be greater than 0. There is no domain for the graph of log x that is less than 0. Now, the difference is my range, which is my set of y values. Well, this is going to keep going up, and this is going to keep getting closer here on the y value, so my range is the set of real numbers, okay? So the domain and the range flipped. And that brings us to what is an extraneous solution. An extraneous solution is a solution that does not exist within your domain. So what does not exist in the domain of logarithms is negative numbers. Let's look at an example of when you get an extraneous solution. We have log base 6 of x plus 9 plus log base 6 of x is equal to 2, and we're going to solve. We have a log equals a number. All of this over here is a log. This is a number, so I'm going to convert it to exponential. Now before I can convert it, I have to condense my logarithm part because I just need a log, one log. Alright, I have a sum, so that means I can use my product property, and I can say, alright, then this is equal to log base 6 of x plus 9 times x. Argument times argument equals 2. Then I'm going to distribute, I'm just simplifying, so I have log base 6 of x squared plus 9x equals 2. Now I'm ready to convert to exponential. So it's going to be my base, 6 squared, equals my argument, x squared plus 9x. Alright, and to simplify just a little bit, this is 36 equals x squared plus 9x. Now I recognize that I have a quadratic equation. So this is not just a simple linear solution, but it's quadratic. How do you solve a quadratic equation? Well, your zero product property is always an option. So to do that, I'm going to need a 0 on one side and all my other things in standard form on the other. So I'm just going to flip this around and put x squared plus 9x over here. Then I would subtract 36 from each side equals to 0. So this was just manipulating it into standard form. Now let me come up here to factor, so I'll have some more room. 9x minus 36 equals 0. To use your zero product property, you're going to have to factor this into two binomials. Since this is a minus sign, you've got a plus and a minus. You're going to have x and x. Now for these positions, I need two numbers that multiply to give me 36 and add up to give me positive 9. So that's going to be positive 12 and negative 3. All right, now I'm going to break it up and I'm going to solve each one. X plus 12 is 0 or x minus 3 is 0. And simple solving, subtract 12 from each side, so x is equal to negative 12. Here I'm going to add 3 to each side, x is equal to 3. So I have two possible solutions that I need to check to make sure I don't have an extraneous root. If I take negative 12 back up here and fill it in, I have log base 6 of negative 12 plus 9. Alright, when I check this, I have log base 6 of negative 3. That already eliminates it because you cannot have a log of a negative number in your problem. So x minus 12 is extraneous. Now let's check the 3. If I put 3 in for log base 6 of 3 plus 9 plus log base 6 of 3 equals 2. I'm going to have log base 6 of 12 plus log base 6 of 3 equals 2. So now I have a sum, which means the product property. So this will simplify into log base 6 of 12 times 3, which is 36, equals 2. Now you can use a calculator to check it, or you can convert it to exponential to check it. I'll just convert to exponential. 6 to the second power equals 36. 6 squared equals 36. Is that true? Yes, 36 is equal to 36. So x equals to 3 is a viable solution. So you have the negative 12, which is extraneous, and x equals to 3, which is viable. Okay, so let's solve this problem acting as if we don't know. We're probably fixing to get an extraneous solution. I examine my problem. I have a log base 9 here and a log base 9 here. They are condensed as much as possible, so I can use my one-to-one property. I'm going to be able to say then 6 minus 3x is equal to negative 2x, and then to solve it I would add 3x to each side, so now I have 6 is equal to x. This is my answer, but because this is a logarithm, I know I need to fill in and check. I'm going to take my original equation and fill this in for x. So I have log base 9 of 6 minus 3 times 6 equals log base 9 of negative 2 times 6. And simplifying, I've got log base 9 of 6 times 3 is 18. 6 minus 18 is negative 12 equals log base 9 of negative 2 times 6 is negative 12. And here's how you know this is no, because it is an extraneous solution. You cannot have the logarithm of a negative number. In fact, if you go to Desmos and you punch in log of negative 2, it's only going to give you a result of undefined. It doesn't exist. Okay, so that's what you do for extraneous solutions. You don't know you're getting one until you go back and plug it in, and you will see a negative answer for the logarithm. And I know I didn't work a whole lot of examples in this section, so I'm going to put up a practice video where I just work multiple examples of solving logarithmic equations, and I will drop a link to that at the end. So if you're interested, you can click on that and see some more examples.